All right, so now we're going to continue working within our vector spaces, and the last special vector space that I'm going to talk about right now is the one called polynomials. Okay, so our vector space V, we're going to write V as equaling, and it's going to look like this: P, okay, N, F. All right, and so P stands for polynomials. N is the highest degree polynomial in the set. And F is the group of coefficients, right? Called the field, but group of coefficients. So what are the coefficients for each polynomial? Okay, so like for example, we write it as, say for example, P2R. It's the most common one. So this is the set of all second degree valued, all right? So we'll take some examples here with real valued coefficients. For example, 3x squared minus 2x plus 1, okay? That is, in fact, a second degree polynomial with real numbered coefficients. 3, negative 2, and 1 are real numbered, all right? So that one works. P of x equal to 4x to the fourth minus 2x squared plus 2. That is not in P2R because that is a fourth degree polynomial, okay? So that's not in there. Now this one, P of x equals 2x plus 1. Well, that actually is in P2R. And the reason why is this. Because 2x plus 1 actually equals 0x squared plus 2x plus 1. Since 0 is a real number, 0x squared, actually it's your second degree term. So this is in fact a second degree polynomial. All right. On the other hand, we might write P of x equal to 3, right? This equals 0x squared plus 0x plus 3. So it is in P2x as well. P2R, excuse me, as well. It turns out that every polynomial that has a degree less than 2 is going to be contained within P2R. Okay? So every polynomial with a degree less than 2 is contained in P2R. Now, a couple things to show. Let's talk about another example. Let's use P4R. Okay? So in P4R, these are all of the fourth degree polynomials. Right? But it's also, in addition to that, it's the third degree ones, the second degree ones, and the first degree ones. So it's all of them. And that's P4R, right? It'll be the fourth, the third, the second, and the first. Okay? There you are. Cool. Now, just like in R3 and R2, okay, well, it's a little bit different, okay? Just be careful in terms of saying that P2R is a subset of P4R, all right? We'll have to think through that one a little bit. I think it might be, which is interesting, all right? Now, what I want to do is I want to show that there is a way to represent polynomials, okay? So representing polynomials using vectors, okay? Okay, so when we represent polynomials using vectors, what we can do is we can actually just utilize the coefficients and make an assumption about the power of x or the power of y or power of whatever it is, whatever variable that we choose is. All right, so what we'll do, say for example, okay, what we're going to do is we're going to represent 3x squared minus 2x plus 1 as a vector in R3. All right, and we'll get into this. We call them isomorphic, but representing a polynomial as a vector will make a lot of computation a lot easier. Okay, so just kind of pay attention to this, right? This thing here, that polynomial, can be rewritten as, okay, as 1, negative 2x, and 3x squared. Okay, right? Notice constant term at the top, right? And then descending order, okay? Descending order for the other terms. Descending order of degree, excuse me, for the other terms. So we start out here at 1, and then we go to negative 2x, that's the x to the 1, then x squared. If we had an x cubed term, say if we were in P3R, it would be the fourth term, okay? So what we can see is dimensional, because its vectors are three-dimensional. In addition to that, right, let's say, for example, we want to represent 4x to the fourth plus 1 half x cubed plus x minus 1. All right. Well, now what I want to notice, this is going to equal 4x to the fourth plus 1 half x cubed plus 0x squared plus x minus 1. All right. And so in this case, right, the constant term at the top, 1, 0, 1 half, 4. Right? Constant, x term, x squared term, x cubed term, x to the fourth term. All right. And so those are some of the key points of looking at the space of polynomials. It's kind of cool that we're actually going to be able to do linear algebra on polynomials. It doesn't just have to be like, straight like physics vectors. We can actually think about them for like abstract mathematical mathematical expressions like polynomials or like matrices. Matrices end up being vector spaces too, right? And so it's kind of cool. We're going to work with this one to kind of help us understand the abstractions, right? But the nice thing about it too is that we can rewrite our polynomials as vectors and work with the coefficient vectors. All right, so that completes the lesson.